Thank you, and thank you also for the previous talks. Were very fascinating. And as said, my name is Kalle Kyyrö. I'm the one of the founders and heading the operations at Smartbi. And what Smartbi does is that we're an agency focusing on artificial intelligence and machine learning, and especially focusing on industrial use cases. And also within that, the energy sector in specific is a major focus of ours. Why I'm also here today. And basically at Smartbi, we focus on we have three main categories where we focus. So first of all, different kind of predictive analytics and predictive applications, different kind of computer vision based applications, and third, natural language processing based applications. And today I'll be focusing mainly on the first one, so predictive applications and predictive analytics. And I will be covering quite a practical use case on utilizing predictive analytics for power grids and how to predict, prevent, and detect different kind of faults and failures for power grids. And yes, basically this is a use case where we have worked a lot with our customers in the energy sector and in more specific in the electricity distribution sector, and have done a lot of different applications and applied AI in multiple use cases in this field.
Kalle, sorry for
yes.
Yeah. So I was just whether you already changed the first slide, because I was only seeing the first slide, but you changed it. Now it works.
Yes.
Sorry
yes. Okay,
for interrupting.
Great. Yeah, and basically it's a very wide topic, of course, how we can utilize AI to predict, prevent, and detect faults that are caused to power grids. And I could cover this topic for hours and hours, but I'll just stick to highlighting a few of the use cases where we have also worked on here, and then I'll cover one of the use cases in more detail. First of all, well, AI can be used to predict different kind of technical failures and the need for maintenance of the different grid components. So we can utilize the past data of the technical failures that have been caused to power lines or transformers or different kind of grid components to predict technical failures in the future as well. Or we can use AI to detect different anomalies in the grid components with both the IoT data that we get from the components of the grid from the grid components, or by utilizing computer vision to actually visually inspect the components and detect any faults, visible faults or anomalies in them, and in this way prepare and prevent faults that might be caused to the grid. Or we might, for instance, utilize AI to optimize the maintenance resourcing to improve the capability to react to different kind of problem situations with the grid, because it's often the responsibility of the power grid companies to provide sufficient maintenance resources and repair resources to be able to react to any failures caused in the grid. And it's thus very important to keep the to optimize and to be able to have the sufficient maintenance resources available all the time. Or fourth, a very interesting use case, which I will be focusing on today, is predicting faults and outages or power cuts caused by natural conditions, which is actually the single biggest cause of different kind of electrical outages. And basically, well, this is a fancy term for storms that cause trees to fall on power lines, or ice that causes power lines to malfunction, or different kind of weather events that cause issues with the grid. And probably one of the best known use case here is the trees falling on the power lines, because that's a major cause of any outages and power cuts. And it's a very, very fruitful ground to actually develop AI-based applications, because I will cover how it can be done in practice in a bit. But basically, we have history of faults caused to the power grid, and then we have weather data. So data of different weather variables, wind speeds, wind directions, rain, temperature, rainfall, all these sort of different variables that we can combine to train models to be able to predict outages that might be caused by natural conditions. And why this specific use case is significant, and why AI is actually beneficial to use in this case. Like I think Mikael said in his speech, that the PNL matters here. So we should find use cases for AI where the economical effect for the companies is large enough. And why it definitely is in this case is that, well, of course, outages, power cuts, they cause major costs to grid operators, such as paying compensations for service interruptions to their customers. Obviously, no one likes power cuts. No one likes power cuts that are prolonged. Customer experience suffers. And third, the preparation that is required to be able to react to the outages caused by natural conditions currently requires a lot of manual work. So basically, the grid companies need to dedicate a lot of human resource to be able to estimate the likely damages caused by, for example, by upcoming storms or very low temperatures or different kind of weather events. So basically, it currently drains resources in so many ways. It affects customer experience, and it has a very direct cost effect. And basically, on a high level, how this can be done. So and how we have also done this and approaching this from two different angles. So basically, what kind of data we need in practice? What data is needed to train the models and for the system to be operational, and how does the technical solution actually work, or how can the technical solution actually work? First of all, the data that we need from the grid area for which we want to predict the faults and for which we want to predict the outages. We need weather observations from history. Typically, it might be something from the past, let's say a few years, at least a year, typically, to be able to cover the different seasonal variation. And this data then we can use to train the models on the other side from the weather side. Then we of course need also history data of the faults caused to the grid, so that we can in a way compare it to the weather observations on the area, and then can train the models to understand that how these different variations in the weather variables, let's say wind speed, wind direction, pressure, temperature, and these variables, how they affect the faults caused. And then basically with this, basically also adding to this grid fault history data, we also need to understand some meta information about the grid and the type of components. So different types of grids and different types of components in the grids are, so some are less prone to natural damage and some are more prone to natural damage. So that's also something that's important to understand here. And then when actually utilizing this system, we need weather forecasts. So the system is based on weather forecasts. And here, what I would like to highlight is that, of course, it's a system that predicts based on weather forecast data. And what that means is that we, of course, need to understand that we may have a kind of a double error here. So weather forecasts, as we all know, they are never 100% accurate. And that, of course, affects the performance of these fault prediction systems as well. Yeah, and then furthermore, it can also be integrated to multiple different grid monitoring and grid control systems to be able to continuously retrain and validate the models. And how technically these kind of solutions can be built is, well, we have multiple different options. We can use some more traditional machine learning regression-based models like random forest-based models or such, or we can use more advanced neural network-based models. It doesn't really matter. We have built solutions that have fared well with both types of approaches. But what I think is common to both of the approaches is that when we are predicting the natural damages to the grid, it's common that it usually makes more sense to predict the kind of risk categories to the grid instead of trying to predict individual faults. All natural events, all storms are different, and it may be very difficult to predict on the natural conditions the individual faults, but rather it makes sense to predict the kind of risk categories. Yes. And to recap on this use case is that well, this is just one example. The prediction of faults and outages based on natural conditions, but it can be, like I also covered in the beginning, it can be expanded to so many other use cases like technical fault prediction, which is also applicable for different underground cables and components, anomaly detection, predictive maintenance, and many other use cases. But it is just one example of those. And also to further highlight this, currently the processes related to fault prediction and prevention and detection, they are very business critical. It's the core business of the distribution companies, but it does require a lot of manual labor, and it thus holds so many opportunities for AI to assist people in responsible and also to even automate different preparation and prediction prevention tasks. Thank you. That's briefly on the use case of predicting and preventing and detecting faults for grids.
Very cool. Thanks, Kalle. Specifically also for going into a more practical perspective here. Just checking if there is anybody having any questions. And there is, just sharing the screen here. Maybe if you unshare yours again, then I can share mine. So the question here is, what changes would you need to make in your technology to apply it to other use cases? Pretty broad question.
Yeah. That's quite broad, but if I would cover it, let's say from this grid point of view and this natural condition prediction point of view. I said we have kind of two sides here. We have the weather damage side here, or the weather data here. We need to understand what kind of weather conditions have been on, and then we need to understand the fault history of the grids. And then it is largely a matter of then changing these data sets apply it to other use cases. But let's say we would expand these use cases to technical fault prediction, then we probably wouldn't need the weather data sets, but could rely on the fault history and then supporting data from other grid monitoring and grid control systems. But basically, of course, the models are nearly always somewhat custom made, but I would say that it does the basic underlying technologies and the basic underlying principles are applicable for many similar use cases.
Cool. Thanks so much.
I think there's one more question in the chat here.
Didn't see that.
I'm going to read it aloud so everyone can follow. As an agency or consultancy, what kind of technologies have you recognized valuable for accessing or interfacing with client data?
That's a very good question. Basically, and accessing and interfacing. I could have a follow-up question to this. So do you mean then not actually, let's say on building the models and building the solutions, but just by accessing the data from the clients?
So wait, was that your follow-up question, or?
Yes.
Well, I guess we would have to wait for users' reply.
Okay.
He says exactly.
Yes. I would say that typically most of the modeling is done quite and the kind of core part of the modeling is understanding the data from the customers, and it can feature multiple different kind of ways to access and for example to visualize the data. And sometimes we may use some ready-made platforms to visualizing the data, but typically it's rather custom made per use case, and I would say that it's difficult to pinpoint a single tool for that, but depends a lot on the use case. Usually it's something quite custom and Python based that we use to visualize and to understand the customer data.
Great, I guess that answers the question. There's one more that Yuri is sharing here from Adrian. DSO sector is highly regulated and at least in Germany not really known for great appetite to innovate. How do you approach and work with DSOs and the AI topics?
I would say that it all comes down to the business case. So we work with a lot of industries that are not very hungry for innovation, I would say, and there's something that we need to work with a lot and face a lot. So basically, as long as our customers can identify a proper business case and proper use case, and we can help them to facilitate the idea on how to maybe utilize AI for that, that's typically sufficient. Because even though, as I said in the question, the sector is not very known for the appetite to innovate, but they still have known business problems and business cases, and then we can help them to facilitate the ideas on how to actually utilize AI on those business problems.
Great. And there's one more question in the chat, actually, by Shubi. I'm just going to read it again. Why have you used an old regression model like random forest RF when there are so many advanced models like CNN or LSTM, etc.? Here, your analysis, what advantage of random forest to see while using RF for predictions?
Yes. That's very nice to hear such specific questions. And I would say that bringing in our lead data scientists would be probably the best bet here, but I'll try to cover that as well. So As I said, we've tried with different kind of modeling approaches. And in some cases, when let's say the data has not been very abundant, so we've had issues with we've had to start off with a limited amount of data. So it might have been so that using different, let's say, these old regression models to predict for prediction might have provided a more robust approach than using, let's say these neural network based approaches. But also comes down a lot to the quantity and quality of data available in this specific use case.